Thanks for the invite, Mike. So time is short. I figured, given the subject matter in the audience, I wasn't going to put together a presentation. I'll just give a little intro, and then we can have a discussion. So a little background on the call and on me. Mike asked me to speak. I guess this is primarily a Bitcoin Core group, about the Bitcoin Core UTXO architecture. To be fair, I'm by no means an expert on Bitcoin Core. I've never made a pull request. Well, I might have made a pull request like forever ago, but never had a commit to Bitcoin Core. I don't spend very much time in the code at all, and I use a slightly different terminology sometimes. So forgive me for that. So it's I can speak in generalities about the architecture and design, but not really too much to specifics. So in terms of what I do, there's a number of people here I don't know. So my background is I have a computer science degree from Rensselaer. I went to the Navy, flew for 10 years, and then came out, started a software company. 8 years later, I sold that to Microsoft. I ended up being a principal architect at Microsoft for a couple of years, which is where I met Philip, who's on this call, and he came out with me, and we did. So I had a spin-out company that was a second startup that's called Beyond Trust. It's still out there, although I'm out at this point. That's doing well apparently, and that was primarily a security company that we sold to Veritas Capital and so on, and did a third startup with Philip, and unfortunately that one didn't work out. And then I found Bitcoin. I had an interest in this kind of stuff going back up to say mid-90s with DigiCash while I was in the Navy, and I even contacted David Schoen. We didn't end up meeting until just a few years ago, but that's one of the reasons why I ignored Bitcoin early on. So I didn't get into this until about 2013, late 2013, early 2014. So I started working on a hardware wallet actually before there were any, before Trezor was out and anything. And I did all the engineering work for that and then set it aside because it was going to be too expensive to make for the market as it stood. So what I did is I kept working on libbitcoin, which is the software stack that I was using. Philip and I were both working on that to implement this thing. And I met Amir very early on because I wanted to work on this. And so I just kept working on it. So presently, we're a little bit of background on libbitcoin. Amir started it, Amir Taki, 2011. It was the first implementation of Bitcoin, of a Bitcoin node after Satoshi's implementation of Bitcoin D. It's never been a fork of anything. It is C++. He started as C++ 11 in 2011. It's C++ 20 now. We went through a number of iterations. I started working on it again around 2014, and when Amir went to grow Java in Syria, I ended up kind of taking over responsibility for it, and have been kind of the person guiding it ever since. And we've had various size teams over the years. So right now there's probably about 8 people that regularly attend meetings and provide support and development. And a number of them are on the call here today. So Amir put out a first version, which he called SX, which was the kind of server product. There was also a client-side stack, and that's all been kind of more rationalized in later releases. That became a V2, which I helped them get out, and then a V3, which is actually the current release, which is over 8 years old. It's not even headers first. There have been a couple of updates just for maintenance, so we have maintained it. But so around 2016, 17, whenever that first release came out, we started working on a V4. Did a couple of years of prototyping on that, and ran into some problems and decided to, well, I not really decided, it kind of slowed down because of the problems. And I ended up writing a book, holding a conference, and that was 2020 in Vietnam. And then came back from that, and started to address this idea of a V4 again. So Philip and I got working on that, and then we had some discussions with some of the other kind of long-standing contributors and worked through the issues that we had discovered during the prototyping. And those almost entirely pertain to use of MEMMAP as our store. So it was the architectural decisions in libbitcoin I have to give Amir most of the credit for. He did a lot of things and adopted a lot of things that everybody else has done since. Not all of them, but like for example, we adopted. I think I integrated libsec before Bitcoin Core did. We switched to level DB very early on before Core did, and then left that for this MEMMAP design. So the kind of high level design decisions were made by him, and so since maybe 2017 or so, we've worked at trying to make those actually work well, because they are fundamentally sound decisions. And so we're kind of getting to that point now, a couple of years of so we have 10 repositories. We're not an application. We're not just a node. We're a developer stack. So we have a build system repository where we do code generation for all of our builds, which Philip has primarily maintained, and that is so we're able to generate all of the build artifacts for a make, CMake, Visual Studio native builds, all of our CI builds, GCC, CLang, Visual Studio, or Visual C++, and Mac OS, Linux, of course, Windows, and so we have a very big build system coverage, and a lot of it all running in CI. We get some more platforms, we'd expand that. We just put out ARM support for Windows, and ARM, of course, we have ARM on Mac. We just don't have a test platform for Linux. So that continues to expand. We have a lot of the low-level optimizations that you see in other nodes, and so the focus has been primarily on the node for the last couple of years, but we do have a full client-side stack as well, and that produces two command line applications, really the server and the explorer. Server is another repo that builds on Node. Node is not really a product, it's something we build and run as developers of the platform, but it doesn't have a public interface. It really only has a C++ interface, and tosses stuff off to text log files. So the server is where people get to talk to the node. Server inherits from node, node inherits from network, network inherits from system, and then node also uses database. So that's the big picture. So where are we? Work on the lower level repositories. So server also inherits from a repository called what's it called, Philip? Every once in a while my brain shuts down. Protocol. So protocol is a ZMQ wrapper. Our public interface is primarily 0MQ, but we in the previous versions we provided RPC, and we'll do that again. So it's been a couple of years working through upgrades to system, network. I didn't even mention the Bitcoin network database, which is where the P2P stack lives, and then protocol database was a full redesign. Same basic architecture, but a full reimplementation to solve some of those issues we encountered. And then it got onto Node a couple of years ago, and started, it completed the implementation, which is pretty straightforward. It's been about, I don't know, about 2 years on performance optimization in Node. And so we've gotten to the point where, so we have a couple of test platforms, just to give you some idea of where we are. Somebody was complaining that our benchmarks were on platforms that were too expensive. So we went out and got a Temu $350 box, And I have a 2.0 gigabits per second internet, but I generally measure about 2.3 on cable. And on that box, just on the Windows, Windows environment that came with it on my network, we do the equivalent. We do things a little differently, but it's the security equivalent of assume valid up to. We were doing up to 850,000 until we just jumped up to 900,000. So most of our benchmarks have been at 850. We try to, just to maintain consistency over time. So we just jumped to 900, but at 850, the theoretical limit at that bandwidth, just to download the wire serialization in one file, would be 34 minutes, I think. And we did it 37 minutes. Fully synced, indexed, stored, queryable, secure to the assume valid. We call that a milestone. So we put in a milestone into the config, and it syncs there if it finds it without having to fully validate it. So I think we just put in 900,000, did a couple of benchmarks, and we're still under an hour at 900,000 blocks. On bigger machines, it doesn't necessarily get faster. I have an 8-year-old machine that I'm talking to you on now. I've been using that since since I started on this project, and that takes it takes a few minutes longer because it's slower memory, slower disk. It's PCIe 3, but it's about the same. And then for full validation on the bigger machine, which is older and slower, but generally has more threads, full validation in about 4 hours for 850K, and we're about 4.5. And we just integrated Taproot, which I'd never done, partially done it before it even came out, but finally got it in. So I didn't want to put out full validation numbers until we had, that validating. That adds about 7%, which makes sense. That's about the percentage of additional signatures you're validating. So it wasn't that big of a difference. So full validation, about 4.5 hours to 900K on an 8-year-old machine with kind of slower threads and stuff. On the smaller machines, the $350, 32 gig machine, it takes I think we're at about 6 hours, maybe 6.5 or 7 for 900K. So also we support, we're fully indexed bidirectionally for all objects in the chain at constant time. Most of it's just direct navigation, but anything that requires a search, hash index search is constant time. And query speed is really the major performance issue. Initial block download gets the headlines, but query speed is tremendous. With enough memory, the entire chain just sits in RAM and is instantly retrievable. So we also index the full Electrum address index, which is about 110 gig. And we also, fully index compact filters, which is another 10 gig. Our store size is about the same size as core, if not smaller. And we always index everything, so we don't really have, except for the 2 optional things, which is compact filters and Electrum. So adding those on, depending on the machine, it can add maybe 15 to 30 minutes to the sync time. If you're validating compact filters, it's really cheap because you're already going through the expensive part. So that's a kind of a summary of where we are in terms of the UTXO design. I've been telling people for years that the bottleneck in Bitcoin D architectures is the UTXO accumulator, right? It's not the store, it's the fact that it's a linear accumulator. I think core people probably understand that, which is why I didn't put a lot of effort into making a presentation to explain it. I think maybe people have questions about how we're doing things, given the fact that we're not doing that. But big picture wise, essentially it's a relational database. It's all implemented through custom. It's a set of C++ templates. It's a very small set originally, but optimization has blown it up some. And those templates are, they have hash map heads, and I don't use the term header because people confuse it with Bitcoin, but we have heads and bodies to the tables. They had to be separated in order to get the fault tolerance we want. The bodies are append only, and the heads are, hash map heads with dynamic access, and they can be resized via config. So essentially, the design produces a relational model, and it's very optimized for specifically for milestone sync and for validation. Less so for query, because query is extraordinary, and it's generally not worth the performance trade-off, the size trade-off to optimize further than that. So that relational model allows us to ask the database pretty much anything you could ask, but we obviously don't index for things like which opcodes are in the scripts, but we index for all the big stuff. So you could do a full block explorer without re-indexing or using another database or anything like that. So the hard problems, aside from the fault tolerance problems that come with using MEMMAP, which can be pretty significant, the hard problems come down to getting rid of order. So the death of performance in modern systems is unnecessary order. And so that's really the focus of the UTXO question, the UTXO store question. So one of the things I did early on was took a look at, what are the absolute requirements for order of processing in Bitcoin logically, not knowing nothing about Bitcoin Core's implementation. I just looked at what I knew about how validation works. And if you want to operate in parallel, you've got to eliminate those unnecessary ordering requirements. So there's no requirement that you download blocks in order, especially with headers first, right? You get DOS protection with the header chain, download blocks in parallel. Validating the header chain can be ordered in extremely fast, so you don't really have to worry about that. We can download and validate in less than a minute. Add some DOS protection to that, and it takes a little bit longer. But so when you get into validating what's required to validate, but we separate the term, and this will probably help the conversation. We separate the term validate from the term confirm, which will be foreign to Bitcoin deep people, but that's because of the different ordering requirements, right? So if you separate the idea of determining whether something is double spent or previously or confirmed previously, you set those questions aside and say, I'm not interested in those. Are ordering questions, right? Did the thing come before? Did it come before more than once? But if you just want to know if the scripts validate, if everything else validates aside from the order, then you can do a lot of things in parallel, right? So the only requirement for validating in that sense of the term is that you have all the previous outputs, right? You've ensured that they're the right previous outputs, and you actually have them so that you can perform validation. You don't have to validate a whole transaction at a time, but it's very a poor performance decision to do scripts without doing all of them in the transaction. So you do a whole transaction at a time, maybe a whole block at a time. All you need is the previous outputs to do that, and the only reasonably performant way to know that you have all the previous outputs is to know that you have all the previous blocks. Otherwise, the indexing cost just goes through the roof, right? So that's how we break it down. We download the blocks in parallel. When we have all the previous blocks for a given block, we validate the block. That means we can validate all of the blocks at the same time, right? I mean, say we downloaded 900,000 blocks and we didn't get block 1 until the very last block. That would mean we would start validating all the blocks as soon as that block came in, which wouldn't be very performant, but it gives you an idea of that actually can and does happen if you configure it a certain way. So what we do is we slice this up into smaller windows to guarantee that we don't go too far without having validated anything. So typically we run with a 50,000 block window. As I understand it, Core runs typically with 1,024 block kind of read ahead download cache, which is a very different thing. We're downloading and storing the blocks permanently. We never delete anything. So except for unvalidated headers, which we just maintain in memory. So we store the blocks, but then when we go to validate them, we have to read the previous outputs, which of course we're reading off of the store through the relational table, which is which is fine. But the bigger question is, how do you, where do you store the blocks while you're waiting to validate them? You can't store them in memory. So they get put on the disk, and then they get read off the disk. So the disk is the disk final storage is the cache, and remember it's memory mapped, so the cache is memory. If you have enough memory, it slows down. If you don't have more, but it still does pretty well as long as you have a certain threshold amount. So all the blocks get stored to the disk. They get read off, not in order, but as soon as they're validatable, they get queued up for validation with the previous outputs, and then the state of each block gets stored. It's kind of an event-driven system, so there's events flying back and forth between these things that are managing order. We call them chasers. So we download chasing, validation chasing, and then confirmation. So confirmation being the final step is fully ordered. That's the only aspect that requires total order, because the questions are ordered questions, right? Does the previous output exist in a block that's been previously confirmed, right, or in the current block? And has some block already spent the previous output? Those are the only two questions that are expensive and need to be asked in order. There's a couple other small things. Most of it can be mitigated during validation, but so making that last question optimal is not easy, and that's really why Bitcoin D has a linear accumulator for UTXOs, because it's not an easy thing to do. And if I was going to build a Bitcoin prototype, that's exactly what I would do. Especially with no data in the store, I would just build a linear accumulator and do everything in order. It's super easy. There's a lot more to it than that. The store has to be fully write concurrent to get that kind of speed. So it's the entire system is lock free. The database stack and network stack is fully asynchronous. The database itself is fully write and read-write concurrent. We can use memory fencing for everything, not even using mutexes for the memory allocators. Although we do use mutexes in a couple cases, and as long as you have enough memory, there's no lock contention whatsoever. It's not even measurable. So that's how you get that kind of speed. You have to, obviously the machine has to be running faster than network if you want to be network limited, and that's our objective, is to be network limited. So, I said we're a few minutes above the theoretical limit, but theoretical limit doesn't include all the other communication that has to occur. So I think we are pretty much at the theoretical limit on a 2.3 gigabits per second network. I don't have a network that's faster than that. We do all the tests off the internet. These are no local tests. So we do other things like using standard deviation to manage peer speed. We rapidly find the faster peers once we've built the header chain, and we manage that so that we're not waiting on peers. We never wait on peers. There's a lot that goes into getting that kind of speed, but in order to get the concurrency, you have to manage the order, and that's really what the UTXO store question is about. Obviously, you need a store to preserve the outputs. We don't prune. We could, but we don't think it's really important. So the performance benefit you get from being append only is far greater than the cost savings you get from saving a few dollars of storage. So that's what we do, and well, I'll just leave it at that. So that's I'm about 25 minutes in. I'd rather allow people to ask questions at this point than talk anymore. So have at it.
Fabian?
Yeah, my understanding of what you said of like when you validate the blocks, I'm interested like how you implement or how do you make sure that you're not denial of service attackable there. It sounded to me, as you explained it, it's probably simplified, like if I withhold one block and then feed you a blockchain that goes like longer than that block and like just feed you lots of bullshit blocks along this blockchain, like at what point do you stop downloading all of these blocks and like ask for that withheld block or detect that in some way?
Yeah, thanks. We use proof of work as the as the DOS protection. So if somebody built a stronger chain than the one we have, then it is, it's the one we want to validate. If it turns out not to be valid, that's fine. We'll take that cost. That's really an inconsequential hit. So I think, essentially it comes down to the same design as pretty much every other node in the modern times when it comes to headers first. We do support blocks first sync as well, and we just basically implement blocks first using the same template that we're doing our header synchronization on. We just, the type becomes block instead of header. Problem there is you don't get the DOS protection. So we maintain a full implementation of all past history and 100% configurable. So you can configure down to that. But with headers first, we don't start downloading blocks until we use the term current, which means there's a huge amount of stuff that's just configurable in a config file. And one of the things is the currency time. So by default, it's 1 hour. So when the strong header chain is within an hour from the computer's current time or the node's current time, then we consider that header chain current. So another thing I didn't mention, and this may help you understand a little bit, is that we maintain 2 indexes of height or of headers, right? So the headers get stored in the header table. It doesn't, valid, invalid doesn't matter, strong, weak doesn't matter. We only try to get the strong ones, the valid ones, but we store them in the header table. Same thing with transactions. All the transactions go in the transaction table. Doesn't matter if they're, they end up, being not valid in a certain block or not confirmed or, pulled transactions. They all go in the same place. So as we're populating these tables, we get a new block in, after initial block download. This is not really much of a different phase. We don't have to move anything, right? We just say, yep, there it is. It stays where it is. So we maintain 2 header indexes, which is a height index. It's basically an array that has pointers to the headers that it's indexing. And one of them is the confirmed index, and one of them is what we call the candidate index. So the confirmed index reorgs from the candidate index so that we are free to do the validation work on the strongest new chain that we see without disrupting the existing chain. This allows us to do deep reorgs at almost no cost. We can and do test reorging all the way to Genesis. And that type of reorg takes a matter of half a second. It just pops everything off, and starts at 0. Bringing it back is about the same cost. So, because the data is already stored and validated and confirmed, and states are persistent. So the candidate chain is what gets built once the header chain that we have is current and it's stronger than the candidate chain, which is on disk, on persistent, then we reorg from the in-memory header chain that we're maintaining into the candidate chain, which is persistent on disk. Then we start, once it's current, which means, close to current time, we start downloading all the blocks that we don't have in parallel. So since we get them out of order, we could, this is one of the challenges we had to work through. We get them out of order. We're kind of inserting blocks into there's really no block table. There's a header table, transaction table, and association table between them for populated blocks, which means we have the transactions, and we start filling those in, but they come in out of order. So say we shut down and we start back up again, we've got gaps all over the chain, right, all over the candidate chain. So we scan the chain and we populate a queue of downloads that we require, and we start doing it again. We very rapidly get full up to speed, and so we start filling in those holes, and as we fill them in, the download chaser figures out the download chaser is chasing the missing downloads, right? So it's filling those in. The validation chaser is chasing the ones that don't have any gaps prior, right? So it's just following up that candidate chain, and it starts validating, and then the confirmation chaser is chasing them in order. And so DOS protection, all right, we could certainly get an invalid but strong current header chain, reorg that into our candidate chain, and start validating blocks and determine that one's either not valid or not confirmable. And then we would reorg down to the fork point between the candidate chain and the confirmed chain, pop off all the invalid blocks, um, um, and start again. That's all. We would end up persisting the transactions that were in that invalid block, but those are fine. Most of, they may all be valid transactions, so they get persisted, and if they get accumulated by another block, that's fine. So the excess cost there is generally, somebody went to an awful big expense to produce 100 bytes of header data in our header table, something like that.
Okay, just to clarify, I had previously understood that you don't do header presync, but you do, it's configurable. You can configure if you do header presync or not. Do I understand that correctly now?
Header presync. Are you talking about DOS protection on the header download?
Yeah.
Yeah. We just haven't implemented that yet. So header,
okay.
We haven't done anything that's specific to DOS protection except for headers first. So our two DOS mitigations that we have yet to implement. The primary one is we just reallocate peers a certain amount of resources, and if they overconsume those resources, they either get throttled or dropped. We don't do any banning. We don't do any tracking of behavior. If it's valid behavior, we allow it. If it's not valid behavior, we drop them immediately. And if they come back, they're valid, we drop them again. It's very fast. It's faster than maintaining, the list, and it doesn't opens up to other types of bugs, which Core has experienced. So in terms of so the second type is what I'm referring to, right? There is the possibility of we don't put headers to the disk until we have a strong current header chain, which means we're just maintaining the actual temporary storage for headers is just a C++ hash map, which indexes the headers by their Bitcoin block hash, and so that creates a natural tree structure, and that basically it's kind of a fragmented tree, right? It just attaches to the candidate chain wherever the candidate chain has a block. So it's basically anything above the candidate chain. So if somebody was to populate a large number of blocks, say below the checkpoints or between the checkpoints, which is very possible, then they could overwhelm the in-memory structure. So what you're calling, presyncing the headers is that DOS gap, but that's completely independent of the database structure of everything I just discussed. It just has to do with maintaining that in-memory structure.
Josie, I see you have your hand up.
I'm sorry?
Oh, Josie had his hand up.
Oh.
Oh. Josie, do you have a question or a comment? Did we lose Josie?
Yeah, his headphones died. He'll be back.
Okay. Sebastian.
Yeah, thanks for the elaboration there, Chris. Sorry, Eric, I mean.
Sure.
I think one thing that kind of clicked for me just now is the amortization of costs that you get between LevelDB's very fast write speeds and its slower read speeds, and a memory map file's potentially slower writes, but to read. So yeah, thanks for that.
Sure. So I don't know. I mean, I'm not an expert on LevelDB, but I don't know that there would be any slower writes. Basically, what happens with our memory map implementation is we're just reading and writing directly from RAM. Directly, there's no overhead. There's paging overhead if you have low RAM, but otherwise it's almost
One of the criticisms that have been raised on the approach of splitting up the blocks by other engineers, not necessarily myself, I think the cost is probably okay as long as the sliding window is big enough, is that you're parasitic on peers who can serve blocks fast on the network. So that the Bitcoin might be parasitic on Bitcoin core nodes because Bitcoin core nodes can serve blocks fast because they're serialized on disk.
So, okay, so I think I understand the question. I'm not sure I understand fully understand what would be parasitic about it, but let me see if I can explain. So first of all, for other people that may not follow the get the context, my understanding is Bitcoin core and Bitcoin D architectures essentially store entire blocks serialized to disk in using the wire serialization. That really primarily exists to provide them to other peers. Otherwise, you wouldn't store them like that. We don't do that. We don't, because that requires redundant storage for everything. Like for example, outputs. That's how you end up with a redundant UTXO storage, which I assume is the case. And it is very poorly indexed. So the purpose of the node is to provide answers to questions, and it's not very queryable, at least not very performantly queryable. So there's a couple of assumptions based in the kind of the parasitic description. One is that libbitcoin couldn't provide a block over the wire as fast as, say, a Bitcoin D on the same network. And that's just not true. The query speed on the Bitcoin is tremendous. And even if you're just serving a block off the disk to somebody, pre-serialized, it's still not, you would have to have way faster networks than are out there, because think about what's happening. We are downloading, parsing, serializing to multiple tables, indexing, validating to even to the assumed valid level, which requires hashing, a lot of costs. We are doing that in real time without adding any additional cost. All of that is happening at the theoretical limit of the download speed that we're operating at. So doing nothing but reading it off the same, in-memory storage and sending it out over the wire is even faster than that. Right? There is no delay caused by having the block parsed. The machine is way faster than the network. And this is also evident in the validation that we do. We're validating, we're downloading, storing blocks in parallel, over the wire, bringing them down to the disk and the previous outputs, and then reading them off the disk to validate them, right? And reading off the previous outputs, deserializing them, putting them in a logical structure, and fully validating them from that point. If that read cost was as slow as you're implying, we wouldn't be able to do that in 4 hours across 900,000 blocks on an 8-year-old machine, right? The read cost is inconsequential. We are something like 3 orders of magnitude faster than the fastest Electrum query indexing servers out there to provide even more data, a lot more data. I've run it. We've got a built-in query that kind of simulates one of those one of those Electrum X type servers. And so there's an assumption baked in there that I just don't believe is true. Second of all, there's also an assumption, in the same area around what core people would call pip speed. We call it top. It's just, blockchain's a stack of blocks, so we call it the top of the stack. But at the top of the stack, we have to validate new blocks coming in as compact blocks. Well, when a compact block comes in, we haven't implemented transaction protocols in V4 yet. We're probably going to ship it with just blocks only mode, and then put in transaction. It's similar to V3, so it's not a real risk item for us. But validating compact block, just to based on the design, I can tell you how it works. Validating compact block means we get the compact block information. We see that we have all the transactions. They're already valid in the context of the compact block, which is going to be true 99.999% of the time, because context doesn't change very often. Fork flags change, median time pass changes, but in a compatible context, most of the time you're going to see transactions are all validated. You validate the Coinbase transaction, you validate the metadata for the block, SIGOP, size, weight, etc., and you're done. There's nothing to store. You just set a flag that says this is valid. So people have said that our approach will be slower when we get a new block in after initial block download. And that's not true. It's going to be a lot faster, because all we're doing is storing a header. That's it. I mean, really, there's very other consequential cost to it. We don't have to. So what I believe, this is just an assumption from the logic. What I see as the logical necessity. I assume that Bitcoin Core, in order to store a block after receiving a compact notification, it has to assemble the block, validate the block, and then serialize the assembled block to disk so that it has this block to serve to other nodes. We don't have to do any of that. So faster at the tip and at least as fast providing the block over the wire to other peers. So parasitic, I don't know. We're going to connect to whatever node is fastest, and we're going to measure that using, like I said before, standard deviation. And we're going to drop slower ones, and we're going to pick up faster ones, because you want to be loading the faster peers on the network when it comes to block download. You don't want to load them when it comes to header sync, right? We do no optimization for header sync. By default, we connect to 100 peers. I've done up to 10,000. We can't really get to quite to 10,000, but you can get like 7, 8. It works fine. I don't recommend it, but just for testing, had to get a new router because broke my router. But the point is, connect to 100 peers. We let them all compete to provide headers. We don't optimize across peers for speed to get headers, so they're competitively providing headers, even if they're somebody's laptop, because we want to make sure we get the strongest chain from whoever's got it. But once we start downloading blocks, we manage peer speed, and we want to attach to those fastest peers. So if a Bitcoin D type node is actually providing blocks faster than other nodes, yeah, we're going to hit that node, and that's what the network should want. We don't want to be loading up slow peers. We want to load the ones that have capacity. And if they don't want to provide that capacity, they should just drop us, which is what we do. That's our DOS protection. We're taking too much. Okay, throttle us or drop us. So I just don't think it's a legitimate concern. It can be managed both on the receiving end, and it's not really a real issue on the delivering end. And I assume what you mean when you said break up blocks was that you would store the data in a more relational manner the way we're doing. That was a big assumption. Yeah, okay.
Yeah.
All right, well, thanks for the question. It's good.
Go ahead, on there.
Hey, so I wonder if you're using just straight up the same P2P protocol, or if you have like any way of doing custom communication if you find another libbitcoin server.
Good question. So yes, we are just doing straight up P2P communication. I'm working on. So we completed all of our node performance optimizations up to this point. I mean, Core's been optimizing for something, I don't know, like 16 years or something. But we've only been doing major optimization work, things that trim, hour off of the sync time, things like that. So a lot more left to do, but we've gotten the big stuff out of the way. So moved on to network work, and in doing some of the, basically we weren't, the current build hasn't been providing blocks or headers to the network. It's only been reading them, which is parasitic, right? For just for the performance work. But now we're turning on those protocols. So libbitcoin as a developer library, or I shouldn't say library, toolkit, it's very modular. So when I say we writing a protocol, I mean like the ping protocol, the address protocol, the block protocol, the header protocol. So we even break it down into blocks in, blocks out, because those can be very different. Ping in and out, same protocol. These protocols are classes that derive from a base protocol class that get attached to a channel, and the channels get assembled by what we call sessions, which are incoming sessions, outgoing sessions, seeding sessions. Sessions get managed by the network stack. So network implements the base level protocols, no transactions or blocks. It just allows you to communicate, get handshake, do a version exchange, maintain addresses, pings, etc., and then do what you want. Node brings in the transaction and block protocols, and then server can kind of, provides the client server interface, but could also add or modify protocols by this inheritance model. So We're just adding to node the blocks out protocol. You know, somebody requests a block, we give it to them, and the headers out protocol with announcements. So what was I going to say? The question has to do with, could we? Absolutely, we could make custom protocols for libbitcoin nodes to communicate with each other. Probably, you know, the way you would do that was you would, you know, we drop peers that send messages that are not known at the current network protocol level. So there's some peers that send out, you know, send out our v2 without versioning it, which is in accordance with the bit, but we drop them because that's incompatible with older peers that actually validate their network traffic. Core actually does version it, even though it's not in the bit. So we would, you know, we would have to have a way to version it properly, which probably mean increment the version number, and then negotiate a message that says you want to do this or not, and then we could do what we wanted. But we're not doing any of that. In the past we have decided specifically not to support certain P2P protocols. We never supported BIP37 beyond the relay flag, which was a break, which is a protocol break to because it changed the size of the version message. But we supported that, but we never supported BIP37. We didn't agree with it. I don't know if we'll ever support Relay, and we may end up writing. You know, we proposed some transaction relay things that we found more interesting than what people call packaging. We may do that if nobody wants to adopt it. We may just do it ourselves. I don't know. But to date, we just use the basic protocols. You know, we have some implemented that are obsolete, like, you know, we do reject and alert. You know, they're off by default. Everything's configurable. So all the protocol level that the node runs at is configurable. Anything that's been deprecated or is optional is configurable. Any fork is configurable. Soft forks, hard forks, undocumented forks, they're all configurable. And we keep pushing that back. We're not back to the beginning of Bitcoin, but we're pretty far back. And so whenever there's a fork to make something simpler in Bitcoin Core, it adds more work to us because we have to add the fork and continue to maintain the old behavior because that's part of our design principle. So we do that with the network too. So I'm saying.
Yeah, Fabian.
Another question, just because you talked about parallel block download quite a lot. I'm curious if you've seen the SwiftSync proposal by Ruben, which would allow parallel block download basically that's compatible with Core. I'm not sure if you've seen it, if you have an opinion on it. Just curious if you do.
Yeah, thanks. I've seen what's been written about it. You know, I tend to not delve too deeply into the technical things I'm not working on. I assume it'll work. And it seems like you know, if it's sound security wise and works, it seems like a reasonable compromise for where Core is now, because, you know, getting to a you know, a node where you can independently do this without that is a lot of work. And you know, it has so it's, you know, if it works out, it might, you know, significantly improve initial block download. And I don't, the numbers I've seen are based on people re-indexing the chain. We don't do re-indexing, so I don't really kind of have an assumption of what that means, and I don't know how that really pertains to, you know, over the network sync that we're talking about. But, you know, initial block download, what we call milestone sync, we don't call it assume valid because we don't really want anybody to assume anything. We call it a milestone because you validate once and then you put the milestone in your config file. You just put the hash and height in the config file, and then if we run across that in the chain, we know that you validated at that point in the past, so we don't validate. But essentially, you know, validation is really what matters. And, you you know, a milestone sync is really just downloading the blocks. Really, you know, you should be able to do it in the time that equals the size of the blocks. And the fact that, you know, Core has been forced to squeeze every block in order so that it can maintain its UTXO accumulator is, you know, kind of tragic in terms of performance for somebody just wanting to download the blocks. But you still have to deal with the validation issue, which is a much, much bigger issue. Because even if you deal with the sequentiality of the UTXO accumulator by having somebody else validate and then give you the state, and then you just confirm the state, which is itself opens up some questions, you still have to deal with the performance issues around, you know, that type of concurrency. How do you get the blocks out of order? How do you maintain the context to validate them out of order? So there's a lot to do there to get to even just I think, you know, the equivalent of a milestone thing. But then also I think you have to end up providing a kind of an automated mechanism for people to upload or store somewhere in a reliably retrievable way their previously validated state for the UTXO accumulator. Because, you know, basically the way the SwiftSync works, the way I understand it, is somebody validates and then uploads their state, and other people download that state, trust it, and then verify it, and hopefully, you know, it's valid, so they don't have to do it again and again. And that means if it's going to be productized, it has to be put out kind of like, I guess, the UTXO, assume UTXO, where you got to put it out somewhere, and, you know, people have to download it and trust it. So there's a lot of negative to that approach. You know, I don't probably need to go over them with everybody. You're probably aware of them, but I think, you know, as long as the security model of it holds up, I think it'll improve. It'll at least improve assume valid speed, and give you the opportunity to do some level of validation in parallel. I personally, you know, I'm not a fan of it. I wouldn't want to do it. It's more, and I think you probably all can understand that it's more of a good thing given where, you know, Bitcoin architectures are, because changing that architecture so you're no longer dealing with a linear accumulator is a significant, you know, architectural change. And it's not like there's any, you know, I'm not aware of any benefit that comes from preserving the UTXO kind of linear accumulator architecture, aside from the fact that it's already there, right? We've done a lot of work on, you know, what, I mean, because it's not, first of all, it's not just about syncing, it's not just about validating. Ultimately, the node is about providing answers to questions that people have. And you know, it's about query performance as well. So, and for us, it's about maintaining the history of all the, you know, all the forks and network changes and stuff. So there's, you know, and providing a developer stack. So there's a lot of design trade-offs that go into that. But if you can achieve the same or better performance by just simply querying for the confirmation state, then there's no downside, right? I mean, we can still prune. You can, if somebody wanted to replace our store, you know, drop in the same store interface and replace it with a slower store that's not append only, you could certainly prune stuff that's been spent. That's not prohibited by the design. It's just a performance optimization decision. So I'm not aware of anything that's achieved by maintaining a linear accumulator, except for the fact that the architectures, you know, already do that.
We got a couple more questions, Eric, if you can hang on. Josie, I know you had your hand up earlier. Are you back?
Yeah, mine's more of a selfish question, just wanting to think through my own understanding to make sure I've got a clear picture of the confirmation workflow. So I think if Stefan has one that's more for the group, you can go first.
Go for Josie.
Yeah, so thanks for the explanation. I think in between like the delving posts and everything, mostly understood what was going on. The one that's still foggy to me is the confirmation workflow. So I'll say some things that are likely wrong. Feel free to interrupt me if I'm getting the terms wrong. But when you're saying validating, it's more just like checking that everything is, it's like checking that everything is ready so that you can kick off confirmation. So it's doing like existence checks and validation.
No, validating means everything up into script validation, everything except. So what happens in the confirmation phase is a totally ordered question, right? We want to know, does the previous output that we previously validated in another phase, right? Does it exist in a confirmed block in the current candidate chain, right? Because we're doing all this on a candidate chain, which is different than the confirmed chain. It could be it could be 10,000 blocks deep and into a fork. So we're working in this candidate chain and we're saying, is it confirmed in the candidate chain at or below this height? And then we're asking, is it currently spent in the candidate chain, at or below this height? Those two questions are pretty much everything. It's not, there's a couple little things, lock time, there's something like that. But those are the expensive questions that are being asked in the confirmation phase. Everything else, script validation, block validation, transaction validation, header validation is all happening in what we call validate. Well, headers get validated independently, right? They have their lightweight validation, and then there's an assume valid milestone sync. We do validate to the extent that we want to prove commitments, right? Witness commitments, transaction commitments to the header, and of course that includes malleability. So once we've proven identity and commitments, that's enough for assume valid. And we of course validate the header chain to make sure that's consistent, and then we attach milestone. When we do validation, all we do is we open up that validation phase, which is doing the commitment checks to the full validation of the scripts, the transactions, the blocks. So it is all being validated in the parallel phase, except for those two final questions, which get validated in an entirely different phase. And that final validation doesn't require the block, right? We validate, we store it, we download it, we store it, we read it, we read the prev outs, we do the validation, and we store the result. That's it. We never read that block again to do the confirmation. All we're doing in confirmation is checking to see if the previous outputs are in the right place.
Yeah, that clears it up for me. I think you mentioned it earlier. You really want to know that all of the prev outs have existed at some point, which an easy version of that is just make sure that all the blocks prior to this one have been downloaded.
Right.
And I think that was the thing I was missing from before. So even though you're downloading and doing things in these 50K windows, the confirmation checks are kicking off once you have a contiguous group of blocks starting from 0.
I mean, you're close, but it just misspoke. The validation checks are kicking off once we have a contiguous set. Because validation requires prev outs, and the only way we could find to efficiently index the fact that we have all of the prev outs required for a given block is to ensure we have all the previous blocks, right?
Yeah.
You could index them, right? But that's a huge cost. There's 2.5 billion, 8 billion prev outs, right? So indexing them for existence just to do that check would be hugely costly. So we don't, because we're doing it out of order, we don't really care which ones we have, and we get plenty. We get hundreds of thousands of blocks ready to validate. We're almost never starved for a block, and that's really the objective of the validator, right? So given that we don't validate transactions independently in this phase, we don't validate inputs independently, we validate blocks as a whole in parallel, right? But in other words, one thread gets a block. That's good enough because we have so many blocks. So I have a machine with 64 cores. I'm validating 64 blocks at a time, and the important thing is there are no gaps, which means there's no real point in maintaining a granularity greater than we have all the previous blocks, right? So the only time we encounter gaps is as we get to the very end of that window. Then we could have a gap as we start another one, but we generally don't. If you're syncing,
So it's starting to make more sense to me, because the validating prev outs one was the thing I think I was misunderstanding, because really before you can say that it hasn't been spent, it's a check for non-existence. But you're kind of getting around that by saying, well, I'm validating and I'm doing the validation and confirm checks once I know that I have ordered blocks, fully ordered blocks, so that the first time I'm writing an output that's kind of saying, I know that it didn't exist yet. And then if it comes up again, you would have a collision.
Yeah, I think you're probably still missing something. Like, let me put it another way. When we go to validate a block, we do not care where the previous output is coming from. It could be from a future block. We don't care. Right? Yeah. It could be it could be an unconfirmed transaction. It does. All that matters is that the hash of that transaction is correct, which we do, of course, validate. So when it goes onto the disk, into the transaction table, it gets shredded out into the inputs and the outputs tables, and those can carry the scripts and everything. All we care about is that there's an identity for the previous output and that we can find it on the disk. We don't care anything about the order of it. We only wait for the order of the blocks arriving. In other words, all previous blocks downloaded, so that we know for sure we have it, so we can kick off that process. So there's the final stage tells us, oh yeah, so we might have validated it using a transaction. We can store 2 transactions with the same hash in the hash table. That's very possible. We deal with eventual consistency. That's one of the ways we get speed. So we could have validated with an unconfirmed transaction, but we might go to do the confirmation phase and find out, well, that transaction was actually confirmed in a previous block, so it's fine. It doesn't matter. It has the same identity, right? So it's less ordered than it sounded like you were implying.
Yeah, I think it's still, I think I'm following. The terms validation and confirmation phase, I think I'm still slightly mixing up. But the confirmation phase is really where you're doing that fully ordered check, which it sounds like at that stage, one of the reasons that's happening so quickly, because like if we take like a pathological example, you're doing all of the download and all the other workflows, but you don't actually get that first block until the very end. So you can't start doing the fully ordered checks till the very end. And let's say you did 34 minutes of download, and then I think the number you said was maybe another 30 or something on top of that, whatever the number, to finish the full confirmation. Well, and the speed.
So this, maybe you're missing something here. When we're doing a milestone run, which is this 37-minute, kind of fast run, we're not doing any of these checks.
Yeah.
We actually run through the workflow because there are other kind of little things that gonna get checked off, but that's an inconsequential speed. So when we're doing a full confirmation check at the end, that implies we're also doing a full validation, right? They're the same security model. We're just doing them in different phases. So we're either not doing any significant validation or confirmation. We're just kind of breezing through these checks and checking identity. That's when we get down to the, basically bandwidth limited time. But when we get into validation, we're doing a significant amount of work to validate the blocks. And then we're doing a significant amount of work to confirm the blocks. We don't do that. And this is the reason I wanted to point this out, because one of the first objections that kind of came up, or questions that came up when it got posted to Delving, was that we're not doing the necessary checks for assumed valid, which we call milestone. And I said, bullshit, you're doing checks you don't need to do, right? And that was eventually accepted, I think, pretty quickly, because all you need to do is check identity. Identity is sufficient to know, right, if you're saying this block is valid, that all the previous outputs are where they're supposed to be, they're not double spent, etc. So Core doesn't do that because it has to maintain the accumulator, right? So it's kind of checking without needing to check because it's building the accumulator. But we don't need to build an accumulator, so we don't care. Everything's in the right places when we're done, and it's all good. So I just want to point that out, because that's an important distinction. When we do get into a place where we're doing full validation and then we're doing confirmation, just to kind of clue you into something that might be wondering, well, how do you do it fast, right? That's a hard question. It's a really hard question. Like the is it in a previous block confirmed question is not very expensive. That's a pretty cheap question. But the is it spent by any other confirmed transaction in the candidate chain is a very difficult question, because that's exhaustive, right? To find any existence is cheap. You just find the first one. But yeah, keep in mind that we store unconfirmed transactions in the same table, right? We store potentially invalid blocks. We store weaker chain blocks, all in the same tables. So for us, it's an even more expensive question. We have to exhaust every possibility of a spender somehow, right, in a query across the entire candidate chain for every single spend, 2.8 billion spends, and we have to do it fast. Well, I can tell you how fast it actually goes. Once we complete validation and we get into confirmation. So the way it works from a threading model is downloads are parallelized by channels operating on independent strands. We use a boost ASIO proactor pattern, but a strand is basically not tied to a thread. It's a sequential, it's effectively looks like single threading, but it's a thread pool, right? So each channel has its own strand, and they're just downloading and storing in parallel. The validation chaser has its own thread pool, which we can vary priority and size independently of the network thread pool, which runs everything else. So then when we get into confirmation, it just runs off the network thread pool because confirmation is sequential, it's ordered, it's linear, so it doesn't really need much power. Within confirmation, we do some queries that span an entire block, and we use C++ aggregate queries to do those, which do get parallelized internally. So when we're doing validation, so in order to achieve this level of speed, when we're doing validation, right, we hit 100% CPU time from start to finish. Very, very rarely see any dip in the CPU time. And then as we, so what you'd expect to see if you're doing one block at a time, even if you parallelized it, is a climb as you build up the threads, right? And then validation at 100%, and then a decline as the threads wind down to 0, right? So you get the sawtooth pattern on each block. Filling in those gaps is what this is really all about, right? We want to continue with 100%. And that's what we get. We get absolutely 100% the whole time, unless we have to stop to flush the disk, right? It kind of can lock everything for a few seconds. But that only happens on lower memory machines. With full memory, it doesn't stop. So this is really about scalability, right? More hardware, more speed. And when that's happening, when we're doing validation, what we're doing is we're pre-optimizing the confirmation. So confirmation, we did run a naive confirmation query that just basically says, okay, here's the block. Let's read out of the block. We got a block identifier. We read off the disk all the previous outputs, or all the points to the previous outputs, right? And then we just run this very big query across the entire table to make sure that every instance of a spend, where the spends are indexed, so we can't just get the top one off of the hash map. We have to iterate through the hash map and get every instance, which means that basically with a 2.
This is where I was getting hung up on it. Like as I was trying to think through how you'd be doing that confirmation workflow. That's the naive.
Right. So it's a good question, because if you got to that point, you understand the problem, right? So if you were gonna do an exhaustive search, right, for every point, which is again close to 3 billion points, and it has to be exhaustive. So the first hit is not good enough. You have to exhaust the entire conflict list for every entry in the hash map table for the spends for every single output. So that's about, if we run at a load factor of around 2.2 to 2.5. So if it's a 2.0 load factor, once you start getting towards the end of the chain, you're doing 2 times how many billion? It's a lot. But on our big memory machine, it's just as fast as the optimized. It's really fast, right? It's hardly, you can hardly tell the difference. So full validation, 4.5 hours or 4.3 hours, something like that. Really not. But the optimization on the lower memory machines takes us from like 20 hours down to like 6. Right? It's a huge difference because we stay out of the this thrashing regime. And the way we do that is by doing all of the work, doing 95%, 99% of the work in the validation phase to prepare for confirmation.
Yeah, so this is kind of what I was curious. In my understanding, when you say like the milestone sync, it seemed like you could kick off a confirmation workflow after doing a milestone sync. Like in theory, right? You have everything there you need to do.
Well, we're doing these run concurrently, right? So we don't like do the sync and then do the confirmation. Confirmation, this is what I started to mention before. Confirmation runs on the network thread pool. It's not, but validation is bound to the download window. Okay, so we're downloading, say, 50,000 blocks, and until we get that last block, we're not going to start downloading the next window. But and we tried it a lot of different ways, but basically it's not downloading tied to downloading, it's downloading tied to validation. So once we finish validating that set of blocks, then we start the download for the next phase, right? So I think that's correct. We originally had that tied to confirmation as well. We ended up decoupling them because confirmation got so fast. So what happens is you're downloading and validating, right? And you want to make sure you fully keep the validator populated. We varied the window size as well. With lower memory, we shrink the download window, and it got fast enough. It doesn't really make a huge difference. So now it's really just to prevent that case where you get that one late block, right? So we're doing all this download, validate happening concurrently, while the confirmation phase is running independently. It's not bound at all to these other phases. So if it sees the next block, it just fills it in. So what tends to happen is because the validator will run on, we tend to run it on a higher thread priority, it'll consume 100% of the CPU time as long as it has something to do. As soon as it has a tiny little gap where it has nothing to do, you might see 10,000 blocks confirmed, right? It just, because they're almost, so the confirmation phase has gotten that fast that we just let it fill in the gaps if there's any CPU time available at all. And so you see these so what happens is if there's a gap in the downloads and the validator's starved, all the confirmation's complete, right? So it kind of tends to cycle back and forth between these phases doing, and what's that all driven by? Ultimately, it's driven by the probability of getting blocks closer in order, right? We do request them kind of in order, but they don't really come in order. So that
was going to be my next question, like how, like the speed windows, and have you varied the different download windows? I'll stop there because we're over time and Stefan has a question. I'd hope we could dig into this a little more. I do want to understand, and maybe I can hop in your guys' Slack and ask more questions, but how you're speeding up that confirmation workflow is what I'm most curious about, because I mean, like you said, it's exhaustive. It's a test for non-existence, really.
If you think about it, you can do most of the query pre-computation in the validation phase, because you already have all the prev-outs already accumulated. You've already got their identities. You've got their parent transaction identifiers. So when we confirm something, how do we know it's confirmed? An output, we look at its parent transaction. How do we know the parent transaction is confirmed? We look at its association to a block. We associate transactions to blocks when they're confirmed in the candidate chain. So that's a lot of navigation, right? But you don't need to redo the navigation. You've already done it in the validation phase. So by short-circuiting, by basically using a little storage, which can be discarded at the end, we can cache most of the state we need for the confirmation phase at the end, and that's what ultimately made it really fast. Basically, and another thing we had to do was we ended up using a Bloom filter on our. I invented my own type of filter, which is more performant at lower load factors than Bloom, but we ended up using Bloom because we needed the higher load factor for space efficiency. So our point table is Bloom filtered for detection of duplicates, right? So we allow duplicates. We can't really stop them, otherwise we lock up the entire thing. So what we do is we have a table of duplicates, and it's usually empty. We do a full sync, unless you stop the node, pause it. Unless you hit a disk full condition, which causes the node to stop mid-block on a few blocks, which get orphaned, you will never have a duplicate during a normal sync. So it's an empty table. If you do that, you might have a few thousand duplicates, which is inconsequential in terms of space. So we do a deduplication, not a deduplication, but a duplicate detection, and we offload these to a duplicates table. So now we know where all the potential double spends are, and it's a very small, usually empty list. And we made that duplication check very performant by using a Bloom filter within the hash map header. It's basically stored alongside the bucket so that we can see if there's a possibility of a duplicate, and that dramatically reduces the query cost. So that was how that was one of the techniques we used to reduce the.
And this is how you're avoiding that full exhaustive, like you're speeding up what would be the full exhaustive search of the spends table to be like.
For that query where you're looking for double spends, that's what there's another approach for the other query. And for that, the double spend query is the expensive one. And if you don't have two instances of a transaction, it can't be double spent. Right. So if you don't have two instances, it's spender, it can't be double spent. So, you know, you get essentially the performance of the accumulator, the UTXO accumulator, right? If you have it, you only have one and nobody else has spent it. So it makes it pretty easy. But because we have to deal with that eventual consistency in order to get the performance we want out of the store, we have to allow the duplicates into the table. And this basically, we just continue, even when we're doing assume valid, you know, or milestone syncs, we have to maintain this duplicate table, because when we start confirming other blocks, we need that information, right, on potential double spends. So even if you got up into the millions, you know, of duplicates in the table, it's inconsequential. You know, it's when you start getting into a billion duplicates that the checks start getting expensive. So yeah, the duplicate table is, you know, just a query, just a performance optimization that it ends up taking, like, you know, on the order of megabytes of data. It's not really that significant. For the other query, we write a cache of the previous output parents, so that, because we already have the transactions of the prev out parents, so we just cache that data, so we don't have to look it up again, and then we just check for confirmation on those. So that's fast too. But yeah, those were not easy problems.
Yeah, well, to me, it's my understanding of the whole problem. That's kind of the heart of it. Like everything else feels, I guess, intuitive to me. Like the parallelization you identified and everything. But the thing, you know, when comparing this to the UTXO accumulator model, how you're getting that performance without the forced ordering that the UTXO model is doing. You're saying, look, if I'm, like you said, you can only have a double spend if you have two instances of the transaction. So if I go through them in order and insert them into UTXO cache and then delete them, that's kind of a way of easily checking the confirmation. And so that's kind of what I was hoping to dig into a bit more, is like, how are you solving that problem? But I think I'll follow up with more questions in your guys' chat.
Okay. Yeah, our Slack is pretty active if you want to come hang out.
Yeah, I've been lurking there for a while. Just the time zones make it hard for me to be there when you guys are there. But I appreciate the walkthrough.
Sure. And we meet once a week, Thursdays.
Stickies, you've been patient.
Sorry for going even more over time. And Josie, the questions you asked were pretty much the ones that I had in mind as well. So I guess if I can just quickly recap my understanding and see if it's right there about the validation phase. So I guess if I understand correctly, you basically, whenever you receive a block, you store it on disk, and then you have probably a single thread that is going to store those blocks into your various transaction and prev tables and so forth as soon as all the previous blocks are on disk. So as soon as you know that you have all previous blocks available, and then once you have each block fully inserted into the table, you kick off one thread per block that is going to do all the validation of the block, because you know that all the references are there, you know that all the prev are there and so forth. So you validate those, which includes script checks and signature checks, because you know all the data is there, and you just assume that there's no double spends happening, which basically does pretty much all the validation work they have to do. And then finally, you have this, I'm guessing it's a single thread that does the confirmation, which then basically just does, you know, making sure there's no double spends, and that's single thread. Is that roughly, or is that correct?
That's pretty close. You know, the threading is slightly different. You know, we have a network thread pool, which comes from the network, actually the network repository, the P2P class. That thread pool operates essentially everything except the validation phase. So in other words, it also includes confirmation, and that turns out to be optimal, because you really just want to be, you want what do you call it, fair allocation between network and confirmation. So that's what we end up. We did have a separate thread pool for confirmation at one point. So everything operates on the network thread pool. Even on my big thread machine, I 64, I run it at 16 threads. That's the default. Seems to work out best. It's a Boost ASIO asynchronous model, so it's very, very efficient. Also, you don't want threads to span kind of different workflows because of thread caching state, you know, at the operating system level. But so that's the validator has a different, you know, different thread pool, because it's all it's doing is validating. And that I tend to run 32 threads on the big and small machines. It works pretty good. 32 logical threads, and that's that has the ability to be jacked up to a higher thread priority. So we can run that at high thread priority, and they basically locked everything, not everything, but locks things out unless it's got some free space. Yeah, that's a pretty accurate description in it. And keep in mind that this is, the implementation is designed to scale, which means more hardware, more faster, right? So we use all the hardware that's available to us. We will use 100% of the CPU if it's given to us by the operating system, and we will use 100% of the memory if it's given to us by the operating system. That's the operating system's job, is to manage those resources. So we don't make any attempt to throttle those resources. You can lower the thread priority, which of course it does give you that effect. I've done talks like this while I'm doing a full sync on the same machine. It works fine. That's right. So you'll notice it if you're running it at high thread priority. And I've jacked up the process on a Windows machine. I've jacked up the process to high process priority, and that can cause, with high thread priority running at 100% CPU, and that can lock you out of your machine for a while. So, so we're trusting the operating system to do its job, and so just that can be surprising to people when they see 100% of CPU, 100% of network, 100% of memory being consumed, and it does cycle back and forth. The perfect world would be all three fully utilized all the time, and that does happen occasionally. But that's the design goal, is to use it all. And if you and it's more RAM sensitive than anything, right? The more memory you have, the faster it goes. Like I haven't found our limit, right? I don't think there is a limit. I think if I had a 10 gigabit per second network, and I had say I have one machine on a Mac with 768 gig of RAM, just so I could test this, and I have a 256 gig of RAM machine I test on. It flushes periodically, but I'm pretty sure if I had like a 512 gig RAM machine, basically would never flush the disk. If I had say this machine that I'm on now, 64 cores, say 500, I probably could get down to 10 minute sync. There's just nothing stopping it, right? And validation, I'm validating on them. Those numbers I gave you, the 4-hour numbers, this is an 8-year-old machine. It's got 2.1 gigahertz cores, 32 dual cores. So if I could just get modern cores, I'm going to get the 3.5. It doesn't have this machine doesn't even have Shawnee, right? I mean, core takes over 24 hours just to do assume valid on this machine, right? Because it doesn't have Shawnee, and it's without that, core grinds to a halt because it's hashing and doing all this stuff essentially on one thread. So Shawnee has a material impact for us, hardware optimization for SHA, but not that much, right? It's not really that significant. But if I had a machine, with 64 3.5 gigahertz cores, 512 gigs of RAM, and Shawnee, we also support AVX up to 512, right? And ARM optimizations for them too. That I'm pretty sure we would be able to validate. We'd be able to sync in maybe 10, 15 minutes, and be able to validate in under 2 hours, maybe an hour and a half. So that's the idea. It's scalable, right? Now people say, well, that's a lot. It's expensive hardware, and yeah, but it'll scale down to smaller hardware. But once you get below a certain threshold of memory, it's going to thrash, right? It's going to be cycling. It's going to be loading table heads off the disk, and so that it can read the index, and then that'll happen with any application at some point. Our point is probably higher than it's certainly higher than Bitcoin D. But if we throttled it down to kind of the speed you get, it's probably comparable. I mean, when we say it thrashes, that just means it kind of starts to approach the speed we see from Bitcoin D, which is like 24 hours, and that's on our take my 32 gig machine, under an hour for 900,000 blocks. On that machine, core takes 14 hours to do 850,000 blocks. So if we dropped it down to 16 gig of RAM, 8 gig of RAM, it's going to start thrashing because most of the memory is going to be used up for table header space, which needs to be RAM resident, and we're going to have a problem. But at the upper end, there doesn't, there's no limit really. And at the upper end, when I run core, I don't do it very often, but I've done a few benchmarks, and I see no more than like 10%, 5%, 2% of my network being utilized. CPU, if it's validating, it can be higher, but it's way, way low. It's just not using resources. That means it's not scalable. That means as the chain gets bigger, it's eventually not going to be able to validate the chain, and so it has to become scalable. That's why we're doing what we're doing, so people can continue to validate. Not just that. I mean, getting synced up is a very important part of the node, but then making the node usable is also important.
Yeah, thanks. That makes sense. And the scalability and parallelization definitely look interesting. So I guess the one maybe downside of this is that pruning storage is not really feasible with this architecture, right? Like you need to be able to store the full chain on disk.
Right. I mean, philosophically, I'm not too keen on pruning because, you talk about being a network parasite, right? That's a pruning node. So also storage is cheap. Terabytes, $25 of fast storage. So, and it's getting cheaper and cheaper every year. So it's not a priority, but we could prune. We just, we get better performance by not pruning, because when you start rearranging your database, yeah, that's a real cost. So you could replace our database on its interface. We actually had some like college kids show up and do some summer of Bitcoin stuff, and actually we're implementing SQLite variant of our database, which never got completed, but that was, we were still working on getting some of these big performance optimizations in. We're like, we might have to deal with a lower memory consumption implementation to get there, and turned out we didn't. So you could prune, if the output's never going to be needed again, just toss anything that depends on it. But yeah, it's not that it can't be done, it's that we choose not to do it because it's not a good use of our resources, given the trade, at least from my opinion, given the trade-offs in terms of cost that are continuously going down, and the network parasite question.
Yeah, makes sense. Thank you very much.
Yeah.